I am Ajit Bhave from Bolt Analytics, and presenting along with me today is Bill Folan, Dr. Bill Folan, who is our chief scientist. I'm not sure how many of you would have heard about Bolt Analytics, so let me just give you a brief blurb about us. We are a tiny startup headquartered out of Mountain View, California. And what we try to do is we try to make the search experience for our customers faster and more relevant. To achieve this, what we try to do is we extract additional insights into the data as the data is being ingested. And we do this by connecting to various data sources which might exist in your environment, various data lakes. It could be Fusion or Solar, it could be Grafana, Prometheus, Splunk, or even traditional databases. And we extract data from those data lakes and pass it through our neural network based models. And from these models, then we derive these insights, which are then stored along with the data, so that when you search for it, you can use these additional insights, and overall the search experience becomes faster and much more relevant. So specifically today, we are going to talk about how we use Fusion or open source Solar, and on top of that, how we have built a real-time streaming analytics which uses our neural network models. The presentation is divided into two parts. The first part is where I will be talking about how we do this data transformation, and we have built a platform around it. Using that, we are able to build these data enrichment pipelines, and they are sent to our machine learning and deep learning models, and how we have an built-in extensibility to add new models, etc. And I'll consider a sample use case of logs analytics, which we have built using this platform. In the second part, my colleague Bill will do a deep dive into our neural models. Some of the models which we have built are around time series, anomaly detection, prediction. We're also working on imaging and voice analysis. So he'll speak more about those. So let's look at our overall architecture. So the first module is an ingest and extract module. So the job of the Bolt ingester module is to connect to these data sources which I was just mentioning about. These could be Splunk, it could be Grafana dashboards, it could be Prometheus, Amazon CloudWatch, CloudTrail logs, or even any other source which might exist in your environment. Sometimes these are traditional databases where you're holding all your product inventory and ordering system and so on. Or sometimes customers stream the data directly to us through various standard protocols or through some messaging system. Once we have taken this data, we pass it through our extraction module. The job of extraction module is to convert this data into a streaming set of data. And typically in the case of when it is, let's say for a time series model, we convert it into a nice formatted time series tree of data. This data then is streamed to a Kafka cluster. So therefore it becomes persisted, and it can be now sent downstream for further processing. And that's where our next stage comes in, where we have a multi-model pipeline, and this pipeline can be configured to do different kind of processing. For example, we have a high performance time series learning pipeline which leverages GPUs, or you could use even the traditional CPU based learning pipeline or imaging service, and even voice learning, different kinds of things. Backing all of this is a Solr cluster, and in the Solr cluster we store all the data which is being ingested along with the learning and insights which have been obtained. So next, moving on, I'll go to the log analytics use case which I was talking about. So just let's take a step back and try to understand what do logs mean. So for example, a very traditional example is system logs. So these could be operating system logs, these could be logs which are coming out of your IoT device or switches and even applications. The second example is access logs. For example, it could be web server HTTP access logs. Every time somebody hits your website, it is logged to the traditional Apache's log format. Or it could be Amazon CloudTrail logs of who is accessing your AWS service at what time and what kind of activity they are doing. Or it could be clickstream analysis, or it could be clickstream logs. So whenever a potential customer is clicking on a product page, that generates a click. So you have now a clickstream of logs. Or it could be transaction logs, which may be coming out of your old company. You may have it in your mainframe. This could be your credit, debit, banking transaction logs, or a credit card authorization. So all these are different kinds of logs, and they all, what we try to do is we then ingest these and pass it through our intelligent ingestion and the extraction module. So let me go a bit deeper into what these modules are. So in the intelligent ingestion pipeline, what we do is that we take the streaming logs which are coming in from your data source, and we pass it, and typically these streaming logs are published through a standard protocol. Many times it is called syslog, which published on a well-defined port and a well-defined format. So we have a receiver for it. It receives these logs and it does some kind of pre-processing. This pre-processing may involve extracting additional fields which may be useful later on for the learning purpose. Once this pre-processing has been done, we publish it as a JSON payload and send it to the next stage, which is essentially publishing to Apache Kafka. So Kafka is very useful. It acts as a processing buffer. It can also handle, in case there are spikes in the streaming logs, it can handle back pressure. Also, in case you want to replay or recover from failure, we can do all of those things. So that's what we use Apache Kafka for. Then comes the bold processor module. The bold processor module, we do something interesting over here. In the logs, what we find is that typically there is a lot of repetitive information. For example, you may have maybe thousands of error messages coming from your logs, but 90% of the content is same and maybe just the error code is different. So we separate that out into common and specialized part, and that has given several advantages. We are able to increase the ingest rate of the incoming logs. Amount of storage required also turns out in Solr to be a lot less, and this separation also helps in the learning part of it as well. Maybe you can learn based on how much time, what kind of specialized messages are coming, at what frequency and so on. So some learning can happen. Once this separation has been done, then we publish it in batches to Solr, to the Solr backend. On solar, to handle the scalability side, we use a time-based partitioning technique because all these logs are time-stamped. So we separate them out into multiple collections, and thereby the data management becomes much more simple. Let's say you want to retire older logs into a longer terms storage like Amazon Glacier, you can do that, and maybe just drop the collections which you no longer use in solar. So it becomes a lot easier. The other thing we do is that a lot of the fields which we extract in the initial stage happen to be only be required during the querying phase. So we only index in solar and not necessarily store them. So therefore, you're not increasing the amount of storage required by that much. Next, let's look at how we extract this this data once it is coming into solar. So there are two types of ways by which we extract. One is we use standard solar syntax, and to which we have added some extensions of our own, and I'll talk about that, what those extensions are in a minute. So we run a predefined set of queries, or you can add more queries at a specific interval, and this query may span a certain time frame. So we have written a custom query handler as a plugin to Solar, and this plugin, what it internally figures out what all collections or shards it needs to go internally to grab the data. It forwards the search requests to the to those collections. It receives the results, and then it collates those results. And at the time of collation, we also apply a regular expression based technique for extracting new fields, which you may not have either indexed or even thought of in storing in Solar in the beginning. So by doing a dynamic way of extracting new fields, you are able to get new dimensions which you extract, and then the final aggregator module can aggregate on these different dimensions, either which are predefined fields or newly created fields. And at the end, you again create a JSON payload which creates a time series of data. So if this is all running on a continuous basis, you are now getting a stream of timestamp data aggregated to different dimensions. In the second method, we rely on the Solar faceting, and as we all know, I think Solar faceting is a very fast way of aggregating the data, because you're relying on the pre-indexing which has already been done in Solar. So here it's again running it at specific interval, but this time we are simply letting Solar do the faceting to do the aggregation, and the net result is again being fed into this same time series stream of data. So at the end of all of this, now we have created a steady stream of data which can be now sent to the analytics pipeline. So how does the analytics pipeline look like? So just to recap, we have taken data from variety of data sources like Splunk, Fusion, Solar, anything else you may have. We have converted through this whole extraction and aggregation process into a set of time series. Now this time series is taken by our neural network based model, and initially these models will run in the training mode, and in the training mode it is going through all of these time series and training itself based on the historical data which it is receiving through the time series. And typically we like at least 6 to 8 weeks of training data to be created through your data source. That we find as sort of the minimum it requires to have a good learning. And for each of the time series, it will save the trained models, and based on how you have configured, or sometimes we have even auto configuring when to relearn, it will, based on fresh data which is coming through the time series, it will update the training models periodically. Once the first set of training models are ready, then the same models now run in the what we call as the inference mode. In the inference mode, it will look up every data point which is coming through the time series, and in real time it will load the training model and it will derive these additional insights which I was talking about. And examples of additional insights could be detecting any anomalous behavior, or it could be to detect or predict something, some event which may be happening. So the inference is producing a set of inference results, and these results are published back to the Kafka data bus, and from then it can be consumed downstream into either in the form of an alert to pager duty or anything else, or you want to publish to Slack, you can take any kind of action. And in addition, we also store these results back into Solr. So you have your repository, which is now data stored along with the additional insights which the models have produced. So we have applied this solution for a customer, and the specific logs which we took were firewall logs. So firewalls log all the external activity which is happening onto your network. So who's all hitting, who all is accessing your network from outside, is there, and what kind of ports or what kind of packets they are sending, all of that is logged in the firewall logs. So we took this solution which I was just talking about, we store all these firewall logs using Apache Solr as the backend, and using the neural network based models, we applied real-time analytics. An example of firewall log analytics is looking for suspicious port scanning or detecting any unusual inbound or outbound activity, or is somebody using spoofing DNS to send out some invalid data. So we have built this use case, and this has been scaled to almost 4 terabytes of logs per day of ingestion. Retention of a quarter worth of these logs. All these logs are being searched in real time during the retention period as the users require. And in addition, these insights are also being stored along with the logs so that customer can take action appropriately. So next, I would like to hand it over to my colleague Bill, and he will do a deep dive into our models.
So I'm going to talk about our deep learning models in Bolt. Deep learning is kind of loosely defined as a neural network that has a lot of layers. So there's a lot of layers that learn various representations of the data. The deeper you go, and so we're applying deep learning to these time series. I'll get into that. We're borrowing techniques. A neural network takes in data and produces an output, obviously. But we're borrowing techniques from supervised deep learning. Supervised deep learning uses labels in order to give examples to the neural network so that it can learn to try to mimic those labels. And it uses those labels to compare its output against, and during the training process, it updates the model weights that are part of the neural network. By doing this in a repeated fashion, it eventually learns a set of weights in the model that actually learns to do the task-specific task that we're trying to implement here. So one example of supervised deep learning is speech recognition. where we take in data that is waveforms that represents somebody speaking, and then a transcript that actually tells us what the words are. And this is, again, supervised in that somebody has to create the transcript that we can use in order to train the model. Another example of supervised deep learning is image recognition, where images are labeled by humans so that we can tell what is in the image, such as a dog or a cat or a house, or maybe more importantly, if these are medical images, an expert can label the images as to whether they're healthy or diseased. And of course, again, that's a very expensive process. In natural language processing, which is something I'm most familiar with, we've developed techniques over the years which allow us to take text in and convert the text into forms of graphs that the computer can understand in order to try to understand the deeper meaning behind the text within documents. So an example of doing that would be a human labels the words in text with their part of speech, which is kind of the first step in understanding human text. And then another set of labels would represent things like predicate and object and subject, the kind of things that kind of abstract to higher level semantic concepts. So again, the network is going to try to replicate these examples that humans give to it, and that in turn allows us to create a model that can generalize later to text that it's never seen. So most of the successful commercial deep learning models have been supervised. So we hear a lot about great success in deep learning. The vast majority of those successes are driven by human-intensive labeling efforts that allow us to give examples for training. Our time series models don't rely on human expert label definition. The reason there is that there is, in many cases, those labels just aren't available. And so we also don't rely on any time series specific tuning. So we have to kind of be ready for any time series that comes at us and be able to process it. Okay. So in the case of forecasting, we don't need labels because the data itself actually gives us the labels. So it's kind of a self-supervised model. It's still the same kind of typical flow, but in the case of forecasting, time series forecasting, we take advantage of a window of consecutive samples in a row, and we can define some of those samples as being from the past and some from the future that we want to predict. And so the past samples become the data input to the network for training, and the future samples become the future labels. And we can process a longer time series by just sliding that window across the available training data, and we learn to train the model for forecasting. So this is a depiction of that process. It's similar to the other pictures, but this is now kind of a self-supervised kind of model. And then when we run the model in inference, of course, we just have a simple history as input and future prediction as output. One of the problems with neural networks is that as you increase the size of the window, they become very complex and require a lot of processing time. And they kind of lose track of the past if you have a very wide window. So a technique that has been developed and expanded over the last probably 4 or 5 years is, another problem is the context can be lost. So we can lose track of the gradients that are used to train the model. So that can be a real problem. So neural networks in the form of a recurrent neural network have been used in order to kind of remember the past history of that window. And in particular, the development of long short-term memory networks is a key aspect to neural networks for processing wide windows and maintaining an understanding of the past history, which is key for forecasting. And then the neural network in this case goes beyond the simple multi-layer perceptron. It goes into a cell that can remember or forget. So the cell can selectively forget or not. It can select what its inputs are, what its outputs are. And this takes care of some of these problems I talked about. And by structuring the neural network as a set of forward and backward layers, we're able to look at the data first forward in what happened in time, and then backwards so that we can get even more information out of the data. And by repeating that as many times as makes sense for improving the results of the model, we create a deep LSTM recurrent neural network. So the other model that I wanted to briefly talk about is the anomaly detection model. So the anomaly detection model is a model, another model that doesn't require labels. So it's an unsupervised model. So it's a network that learns what it needs to from the data, and then we later apply it in inference. So without the labels, well, let me also just step back a little bit and talk about what an anomaly is. So everybody kind of has a concept of what an anomaly is, but there's a kind of a reasonable definition of what they are. An outlier anomaly is an observation which deviates so much from the other observations as to arouse suspicions that it was generated by a different mechanism. So that's kind of general enough that you could apply it to many of the cases that you think of for anomalies. The use of this is, there's many uses. It can be used for intrusion detection, credit card fraud detection. In the Internet of Things, we can identify interesting sensor events. Medical diagnosis or failure detection are some examples. Okay, and here's an example of what a time series looks like when it's annotated with anomaly detection. So this is an example that is it's pretty common, made available by Twitter. It represents the number of uploaded photos to their site, and then they've also added some synthetic anomalies to it to make it interesting. But it kind of demonstrates what an anomaly looks like and how you would identify it in a time series graphically. So in the case of anomaly detection in time series, what we do is it's a similar process using windows. So we break up the time series itself into a series of windows, and use that in order to generate our training data. And then we again later do the same thing when we're forecasting and running it in inference. So the window defines kind of a space where we're interested in temporal anomalies. So anything that happens within that window can be considered an anomaly if it's unusual. So an anomaly doesn't have to be a large excursion in one sample. It can be a pattern that occurs within that time. And then it can also, we also want to understand point anomalies, which are rapid excursions that are more easily visible in the time series by a human. So time series is you can think of it as three components. There's the first component is the nominal process. So that's the thing that's happening that it's the kind of the normal process that's happening, and we don't really care about the normal process, but it's a big part of the signal, hopefully. And then there are also anomalies that we really care about a lot. And in between, there's noise. And the noise is there because nothing's perfect. There's always, the nominal process is going to have a little bit of noise associated with it. And even the model can generate a little bit of noise in the process of executing. So you can think of the signal as being composed of these three components. So the neural net really needs to estimate the nominal signal. So it's called an anomaly detector, but it's actually it's trying to predict the normal signal or a nominal estimate. So it does that by looking at the time series and extracting the normal behavior, and it does that by noticing the regular behavior over time. So a good structure for doing that, instead of the bidirectional LSTM, is a neural convolutional autoencoder. So this now uses a different architecture, but it works really well for anomaly detection. It divides the neural network up into three parts. The first part is an encoder. So we take the original signal and encode it into this abstract representation. The abstract representation is a smaller, it's a shorter representation than the actual input. So then we decode that when we're done. So by doing this, it forces the model to create a representation that just remembers the important parts of the signal, and it forces it to discard the unimportant parts of the signal, which is what we want. We want to understand the nominal signal. So this is kind of it uses the same training data as for input and output, so it doesn't require labels, and it learns the nominal process. So once we've learned the nominal process, then we can go back to our original theory here that we have three parts to the signal. We can subtract the nominal from that, and we're left with just two parts now, the noise and the anomalies. Now what we care about is the anomaly, so we have to get rid of the noise. But from the distribution of the result, the noise usually is very easy to spot. It just needs to be bounded. It's not going to be a perfect Gaussian distribution like I show here, but it can be similar, and it's clustered around a mean. So we can do just the normal kind of statistical analysis, find the mean and standard deviation of that central node, and find the limits, and then we can say that, okay, everything outside of those limits is an anomaly. If it's outside of the limits to the left, it's a negative anomaly. If it's outside of the limits on the right, it's a positive anomaly. And that allows us to say, okay, how far away from that central node is it? And that lets us give a score to anomalies. So one anomaly is not necessarily as bad as another. This gives us an idea of what the degree of anomalousness of each data point is. So in the case of the port scan use case that Ajit was talking about earlier, we analyzed the firewall logs and turned those text logs into a stream of values, and then the anomaly detector takes that stream of values and identifies the anomalies. Then we can present it to the user, and the end result looks like this. So we'll open it up to questions now. Anybody have any questions? Yeah.
Do you have any other models than anomaly detection?
Yeah, so we have forecasting models, and we also have done some image recognition, and not on log data. No, it's a different application.
Yeah, we are also working on adding univariate and multi. So this is univariate. Bill's also working on adding multivariate models where you can take multiple parameters together and then see how they interact with each other and produce the same kind of anomaly. So that is useful when you have parameters which are kind of related to each other.
From different sources, so multivariate from different sources. Yes, that's what Ajit was just talking about. So that's one of the powers of a neural network, is that you can compare. You can use a bunch of different signals as input, and then the correlations are determined by the network over time just by learning them.
Do you have any Indian case studies on your website? Like, I'm trying to understand
Yeah, we do have. Yeah, the question is, do you have any more case studies? So actually, we have a booth. Please do stop by if you have not, and we can share additional material with you.
Okay, well, thank you very much.
Thank you very much.